This hit and run econometrics is on generalized least squares for heteroskedasticity. And the theme is two cheers for GLS. Let's see why. We're going to do a subcase of generalized least squares called weighted least squares. There we go. Weighted least squares. A subcase of GLS. Remember, generalized least squares meant that we transformed the data and the errors in such a way that they would meet the Gauss-Markov assumptions, and then we would just use ordinary least squares. Well, let's see how this might work when we have a heteroskedastic error. Suppose, for example, that our error term is equal to ui times zi. Okay, ui times zi, where, okay, ui is a classical error term. It has all those desirable properties about the zero mean, and most importantly, it doesn't have any heteroskedasticity. Classical error term. And zi, there we go, zi gets bigger as the error gets bigger. Zi could be anything thought to be associated with the error. When you get to know a data set really well, then you just look at it and you see, oh, wow, there's a variable that really gets big when our errors are pushing us a long way away from the line. So then what we do is to rewrite our basic regression equation as yi is equal to beta 0 plus beta 1 times xi. We'll make it simple here. And now where we would write epsilon I, we write this assumed form, ui times zi, just like that. Notice what happens if we divide by zi. And we get, oh, this is so neat. You get, well, let's just write out the equation there, make sure we know what we're doing. Beta 0, beta 1 times xi plus ui times zi. See how we're making room for everything here? Look at this. When we divide through by zi, then what we're going to have is beta 0 divided by zi, and for notational convenience, we'll just make that 1 over zi. See, that's beta 0 divided by zi, just like that. Plus beta 1 times xi over zi. And wait for it, here is where the magic happens. Look what happens. We divide zi by zi. Hey, that's just equal to 1, so it goes away, and that means that we get just a really nice ui as the error term of this transformed equation. So we would say ui is not heteroskedastic. See that? ui is not heteroskedastic by assumption. Epsilon I was, but this ui is a very nice one, and we just use OLS. There we go. What could be neater? Well, you notice I said 2 cheers instead of 3 cheers. The old British naval movies, it was always 3 cheers. This time we're withholding a cheer. And there are a lot of reasons for this. I'll give you the most important reason first is you don't know that epsilon I equals that. Hey, if epsilon actually equals ui times zi squared, then dividing through by zi is not going to get rid of the heteroskedasticity. If it's equal to a zi to the 1.5 power, not going to get rid of it. If it's equal to some really complex function of zi, then we're not even going to get close, because you notice zi gets bigger as the error term gets bigger, but this only works exactly if epsilon I is equal to exactly ui times zi. But in addition to that big reservation that says, okay, we don't really know that this is a better estimate because we don't know the functional form of the error term. But in addition to that, there are a couple of quirks which provide sort of an opportunity to consider how we're actually going to do this. One thing is that the equation as transformed has no constant term. See that? It's got a coefficient on 1 over zi, but it doesn't have a beta 0 sitting out there by itself, so it does not have a constant term. So here, beta 0 is the coefficient, okay, the coefficient on 1 over zi. We have that. And then beta 1 is the coefficient on xi divided by zi. And it is actually the original beta 1, which is usually the thing that we were trying to estimate anyway. Remember, the constant term is a garbage collector. We're not going to trust the estimate of beta 0 anyway, so we're not especially worried about that. And now, the one additional quirk about this 2 cheers for GLS that I wanted to show you is the whole question of, well, if we're serious about this and we really want to estimate it with no constant term, how do we go about doing that in R? Well, let me just show you just a little case study here, because I asked myself the question in getting ready for this class the first time I taught it. What I would do is I would just do a search for R, no constant term regression. And here's what I would get over there at Stack Exchange. Somebody answers the question and says the formula, there it is, linear model, there's the thing that we do right there in R, will include an intercept by default. That's what we've been doing every time. We didn't have to tell it to go estimate beta 0. It was doing it by default. The formula, so here's what they're saying to do. Y tilde x1 plus x2. Look at that, plus 0. Plus 0 just mathematically wouldn't do anything, but in R, that plus 0 is a way of telling R, go estimate an ordinary least squares model without an intercept. Now, before we go hauling off to go estimate that without an intercept, here is one more thing that I would have us look at. This is in your Studeman textbook. It's over there around page 190 or so. And here is some unequivocal advice. Do not suppress the constant term. You see, Studeman is really fond of the constant term, and he would say that all those times when you force the constant term to equal 0, which is what you're doing if you're doing this with R, you're actually making a mistake and getting rid of the good properties of the garbage collector. So when we put all that together, what we see is we've got weighted least squares as a subcase of generalized least squares. It is a way of getting rid of the heteroskedasticity, but it's got so many quirks to it that a lot of people go for an alternative method that we'll talk about in class. So on second thought, maybe it's not even 2 cheers for GLS for heteroskedasticity. Maybe it's just a cheer and a half. But in any event, there is generalized least squares for heteroskedasticity.